Today, I'll be presenting our work on Apex MR, a framework for multi-robot asynchronous planning and execution tailored to cooperative assembly tasks. Let's begin by comparing a single and multi-robot assembly. There are a lot of existing work using single robot to perform numerous tasks. Despite its capability, using a single robot is limited by its reach and efficiency. They also have limited dexterity, which makes them unsuitable for many types of assembly tasks. By contrast, multi-robot systems can cover larger workspace, improve assembly efficiency, and handle more complex tasks through cooperation. Multi-robot cooperative assembly faces key challenges. We need to ensure safety such that robots do not collide, manage any uncertainties in execution due to controller delay, and addresses planning scalability for large assemblies with hundreds of components, all while maximizing the efficiency and throughput of the assembly. Our method, Apex MR, or Asynchronous Planning and Execution for Multi-Robot, starts with the following input. They are the environment setup of the robot and available blocks, the assembly design, and the library of manipulation skills. We also assume that an assembly plan can be found. Our method needs to make many decisions to achieve the objective of safety, efficiency, and scalability. The algorithm must automatically assign robots and objects to each task, find valid grasps and support poses, and coordinate collision-free trajectory. On a high level, Apex MR first generates a sequential task plan, then passes to a motion planner to generate a sequential motion plan, and finally converts to a TPG for asynchronization. For task planning, tasks must be divided among multiple robots. Each task must also be assigned an object and associated grasp pose. Some tasks require coordinated support from two robots. All of these decisions are solved with an integer linear program. In the sequential task plan, each robot starts from its home pose, then transits to pick the object, place the object, and finally back to its home pose. Only one robot is moving at a time, while the other robot will be waiting at its home pose. Then, the other robot starts picking the next assembly step and finishes its pick and place. We also add a task dependency to ensure that the green robot must place his BK before the blue robot can place his BK plus 1. Given the sequential task plan, the robot paths for each task can be planned with a single agent RRT Connect planner. The next step of our method is to build a partially ordered graph on the robot paths to capture the motion dependencies between the robots. We call this a multimodal TPG. The first step is to add all those pose nodes for transit trajectory and a scale node for every other task. Edges refer to precedence constraints, meaning a robot can only move to the next node if nodes from incoming edges have been completed. We add type 1 edges for consecutive nodes of the same robot. We then copy the task dependencies in the task graph as type 2 edges in the TPG to ensure those precedence constraints are still followed. Then, we iterate over all the pose nodes to identify any collisions, and add corresponding motion dependencies. Since TPG is a graph, each robot can schedule the action to execute in parallel and asynchronously, as long as each robot waits for its incoming dependencies to be satisfied. The shortcut is a linear interpolation that must be collision-free with the environment, and must avoid any other robot that it can potentially collide based on the TPG. If the shortcut is valid, we use it to update the TPG. This process can be repeated until a user-defined time limit is reached. During execution, a central server is used to monitor the progress of all robots and control the scheduling. Each robot has its own controller sensor feedback loop and receives its command from the action queue. The central server sends all actions that are safe to be executed to the robot's action queue, which are all the actions up to any unmet dependencies in the TPG. As the robot completes actions, it updates its status back to the central server, and the new actions that are safe can be added to the action queue. As mentioned earlier, our proposed Apex MR assumes the environment configuration is provided. We apply our method to a bimanual LEGO assembly scenario, where the environment includes two robot arms, a LEGO base plate that is placed between them. Each robot is equipped with a force torque sensor. The robot uses the end effector tool to manipulate the LEGO bricks and build customized LEGO structure on the base plate. Also, Apex MR assumes a predefined robot manipulation skill library is provided. Specifically, in the LEGO assembly task, we designed the robot to have these different manipulation skills. The robot can use a tool to disassemble and pick up a LEGO brick, assemble a LEGO brick by placing it down and release it, support under to provide extra support to the existing structure, hand over a Lego brick to another robot and reorient the brick's orientation in hand. Assemble a Lego brick by pushing it up and release it, and support above bricks to provide extra support. We evaluate our method on the following 9 Lego assembly tasks. Our tasks have both long horizon assemblies, fragile structure that requires collaboration, and lastly 3 complex structures. We compare our Apex MR to 2 baselines. The first one is a turn-based sequential motion plan. The second is a synchronous plan, where each robot waits for other robots to complete the current tasks before starting the next task at the same time. We use 2 metrics to evaluate the performance of Apex MR. The first is make span, which is the total time from start to end for executing all of the robots. The second is wait time, which is the amount of time any robot spends waiting instead of moving. We first compute the make span of sequential planning, which we normalize to 1 and plot on the dashed blue line. Synchronous planning performs a bit better than sequential planning, but the wait time can still be significant. If we can convert the sequential plan to a TPG, the make span is significantly reduced and lower than the synchronous plan. We can also convert the synchronous plan to a TPG and achieve similar performance. Lastly, if we add some shortcutting, the make span and wait time can be even further reduced, almost halved compared to the initial sequential plan and reduced by more than 30% compared to the synchronized plan. The wall clock time for each component of the sequential plan and sync plan are shown respectively. Note that the synchronous motion planning is significantly more computationally expensive. To further demonstrate the capability of Apex MR, we deploy it to a real dual industrial arm system. These 2 videos show the system building the vessel and guitar structures, which are long horizon assembly tasks with 36 and 24 steps. We can see the Apex MR can safely and efficiently coordinate the robots to efficiently accomplish the long horizon tasks. In addition, we use a dual arm system to construct more fragile structures. We can see the Apex MR can coordinate the robots to collaborate together and use the robot skill to accomplish the complex structure. Specifically, since there are multiple operations on overhanging structures, we see the 2 robots can collaborate and provide extra support when needed to achieve the complex assembly. Finally, we use a bimanual system to construct the character of RSS, which are complex and delicate that require sophisticated collaboration. We see Apex MR can safely, efficiently, and robustly coordinate the robots to construct these complex assembly tasks. A major limitation of the system is the system robustness in the manipulation policy. For example, due to the fragile nature of the static Lego connection, the robot can fail to assemble these steps and may require human intervention. Another limitation is that all computations are currently done offline, and we plan to extend our framework to be able to replan according to changes or new tasks online. Thank you.